Let's discuss now some other benefits of virtualization. One interesting thing is that once you are able to virtualize your hardware and through an hypervisor run several guest operating systems and processes within each guest operating system, you can do something you could not really do before, and it is related to multi-core CPUs or architectures in which you have actually multiple CPUs. Okay, what you can do is that you can dedicate a specific subset of the cores of one CPU, or maybe a subset of the CPUs, to a specific guest operating system. And that has an interesting implication that is something that did not really exist before virtualization. You might end up in situations in which the program you're writing and later executing as either a set of processes that are communicating with inter-process communication at the OS level, or most likely a multi-threaded process, can have a parallelism degree that is actually fitting the number of physical cores you have in your virtual machine. So in that case, you might be able to do some optimization at the code level that is very specific to the number of cores you are going to use, because now you know how many cores you are going to use. It's for a specific virtual machine that will run on a specific hardware. Okay, if you think about large industries like Google, where they have a lot of servers and they might have some specific applications that are running, then they can make versions of these applications that are really taking advantage at the, let's say, optimal level of the resources of each virtual machine once they associate a specific number of cores or CPUs to that virtual machine. The other nice property of virtualization is that of the duplication. The duplication is something you usually do for the file system. I'm not describing it now in too much detail, but the basic idea is that you can create a sort of middleware or a layer in your file system that, before writing each block, checks whether that specific block is already stored. Maybe it belongs to a different file, but is already stored on the disk. Okay, you do this basically using hash functions. So if you keep for each block its hash, and you have a registry of all the hashes, when you're trying to write a block and you already see that its hash is registered because it has already been written as part of another file, then instead of actually writing the block, you just keep track of the fact that that specific block of that specific file is actually found somewhere else. Now, this kind of deduplication, now you can do it even at the memory level. It's not really surprising if you think back at virtual memory and copy on write mechanisms. At this point, it should be clear why you really want to decouple the logical representation of memory from the physical one. The example here is that of an hypervisor running a set of operating systems. If you think that all these operating systems might be actually the same operating system, it means that all the text portion of the processes that belong to these operating systems, the one of the operating system, not the user process, they will all be the same because it's always the same operating system. So you can play this deduplication at the memory, keeping only one copy in the physical memory of, in this example, the parts that belong to the operating system, while letting believe each operating system that it has actually its own copy of the memory. So it's exactly what you do with the processes when you do copy on write. Now you can do for entire operating systems with the duplication of the memory.